Yeah, welcome to our talk about the influence of waste sterilization on plastic properties. My name is Andreas Felber. I'm from MACS Sterilisationsanlagen GmbH. We are a company that is building medical waste sterilization systems. Why do we have to talk about this topic? If we think about medical waste, for instance, we are talking about hazardous waste because it's infectious waste. So before we can go to a subsequent recycling process, we have to think about how we can make this waste safe. And this is where our technology counts. And this leads us to our first subtopic. I would like to introduce our sterilization system, our so-called MACS process. It all starts with the medical waste that enters the machine via the hopper. After the hopper gets filled, we will close and seal the machine so it's air and pressure tight, and then the shredding process starts. We are shredding the waste because of two reasons. Reason number one is we want to decrease the volume of the waste, and the second and main reason is we want to increase the surface of the waste, so this increases the effectiveness of the sterilization process that follows afterwards. After shredding has ended, the waste has entered the autoclave that is below the shredder. And we have an auger screw inside this autoclave that ensures the even distribution of the material inside the autoclave. Then we are creating a vacuum. This means we are sucking the initial air out of the machine. This is necessary that the steam can reach every waste particle. If you have some air inside the machine, the steam cannot reach the waste particles that are in this enclosed air. And during the whole process, we're constantly moving the material with the auger screw to ensure that the steam can reach every waste particle and to prevent sticking of the waste particles together. Then we are starting the so-called fractionated vacuum. This means exactly what I told you before. We are sucking the air out, adding steam, and we are doing this a couple of times so that no initial air remains inside the machine. Then we have to hold temperature and pressure for a certain time. This is where the actual sterilization takes place. And after the sterilization phase, this is the horizontal line in the graph on the right side, we're releasing the overpressure. We're creating another vacuum again to get some moisture out of the waste. And then we have a pressure equalization again, and then the lid of the autoclave opens and the auger screw feeds the material out of the machine. What does this mean to the waste? If you're not doing a MACS process, your waste stays dangerous and bulky, and it can contain liquids. Think about bags or containers that contain body fluids. We're cracking these bags and containers with our shredding process. And we're also sterilizing these liquids, and they are after the process gone because they will go to the sewer, into the wastewater stream. And because of these first two things, the handling of the untreated medical waste is quite complicated, and you have pretty high disposal costs. Because when you go for a transportation process, you're transporting dangerous goods, and this is quite expensive. And most important thing, you have to go for a high temperature in incineration to get rid of the waste, which is quite costly as well. After the MACS process, the waste is non-hazardous. It's comparable to normal household waste. All the stored liquids are gone, and the volume got significantly reduced. This means we have a pretty better handling of the material, the waste, and of course the disposal costs are much lower now because now you can go for recycling or you can go to a normal waste to energy incineration plant. And most important thing, we are now ready for a recycling step. And we're achieving all this with a proven sterilization process. We have an independent microbiological laboratory that proves our sterilization effectiveness according high German standards. But let's go to the main topic of the day. We did all the testing you will see on the following slides within a public funded project. And we had several partners we were working with. And we've chosen some material that is typical for medical waste. For example, Petri dishes made out of polystyrene or pipettes made out of polypropylene, and we always had a virgin charge of material. This is our charge we can compare with, and then we treated the polystyrene and we treated the polypropylene. But yeah, let's have a look what happened. First, we did the differential scanning calorimetry. What does this mean? We are looking on the oxidation onset temperature. This is the temperature where the decomposition of the material starts. And you see untreated material has a higher oxidation onset temperature than sterilized material. So something happened to the material, which means we had a degradation of the material. But an important thing, this does not necessarily mean that relevant properties will change. For example, mechanical properties. You see it for polypropylene and also for HDPE, that the Young's modulus, for example, the tensile modulus, does not drop. Yes, we have an oxidation, a degradation of the material, but it had no influence on the Young's modulus. Almost the same picture when we go to tensile strength, we had a slight drop for the polyolefins, but yeah, a greater drop for polystyrene. And we had some changes when it comes to elongation at break, mostly for HDPE and polystyrene. So how can we sum up these first results? Yes, we can see a degradation during the autoclaving process, but once again, this does not necessarily mean that mechanical properties, for instance, will change. But for some materials, for example, polystyrene, we could clearly see a drop in mechanical properties. What does this mean? If we want to create high-value recyclates out of it, we have to do something with the material. We have to enhance the properties. We have to restabilize the material. What have we done? We did some additivation. We put some additives, mainly antioxidants, to the polymers, and we always had the formulation. This is F1 and F5 with no additional antioxidants. It's just the treated material, and then we had different formulations with different mass fractions and different antioxidants. And let's have a look what happened. First, the oxidation behavior. Yeah, a clear picture. With an increasing amount of antioxidants, we have an increasing oxidation onset temperature. Once again, this is the temperature where decomposition starts. Or for antioxidants, more relevant, the oxidative induction time. This is the time that is needed before decomposition starts. Here we have a constant temperature, and then we're measuring the time until decomposition starts. And you can also see the more antioxidants you have, the longer this induction time takes. Same picture for polystyrene. You could also see a higher amount of antioxidants means a higher oxidation onset temperature or a longer oxidation induction time. Interesting is for formulation F9. You do not necessarily need a large amount of antioxidants. Sometimes it's just the good choice that decides whether you have a good effect or not. So yeah, it's important to choose the right additive for this. There's another thing where you can see the effectiveness of antioxidants, or where you can check whether degradation has taken place or not. This is the so-called carbonyl index. Carbonyl groups are forming when degradation takes place. So the higher the degradation is, the higher the carbonyl index is, just in short. And you could see a clear picture here. Once again, the higher the amount of antioxidants is, the lower the carbonyl index is. This means the lower the degradation was. Almost the same for polystyrene. Here we have a special polymer effect because sometimes the antioxidants are hindering, or the antioxidants are also forming carbonyl groups. So this is why the curve looks like this, but basically it works. But yeah, I'm an engineer. I'm more interested in this stuff, mechanical properties. Let's go to impact strength. You could clearly see the higher the amount of antioxidants, the higher the impact strength becomes. But You can see this when you look at formulation F7. There is some kind of optimum, some kind of optimal mixture. So it's not only increasing the amount of antioxidants, it's just choosing the right combination, and then you can have a significant effect. Let's go to other mechanical properties. Here, ultimate tensile strength. We could clearly see that it's possible to enhance tensile strength, but to be honest, it was not that big as we expected it. So this means some homework is left to do for us, to do some further research to maybe get a better effect. But basically, it's possible to enhance also tensile strength. What else? If we look at elongation at break, same picture here. There is some kind of optimal formulation and also an increasing mass fraction of antioxidants leads to a higher elongation at break. A different picture occurs when we look to the tensile or Young's modulus. We can see that maybe the best formulation for elongation at break is not the best formulation for Young's modulus. So it depends what is the most important property you want to enhance. But we can clearly state that having any kind of antioxidant is better than not having any additional antioxidant. You see this when you look on formulation at 5. It's the lowest value. So it's definitely worth thinking about antioxidants. How to sum this up? We could clearly see a positive effect of restabilization, and it also does not positively affect the oxidation behavior. And the oxidants are mainly, the name tells us this, mainly for improving the oxidation behavior, but it also improves mechanical properties. We could clearly see this in these tests. We could clearly see a lowering carbonyl index. So degradation is really delayed. And especially for polystyrene, it worked very well. I didn't show you mechanical properties from polypropylene because in our first tests, I showed you that sterilization had no negative effect for this kind of material. This leads us to the last 2 slides. We want to do further tests because, we didn't learn all the effects that are worth to be learned. And when you think about medical waste, you have a great variety of materials. So we want to take into consideration more other materials, and we want to do more other tests. We want to do thermal tests as well, the oxidation behavior. We also want to do spectroscopic tests again, but we want to do the so-called Guild permeation chromatography. This is some kind of direct measurement of degradation. Here you can see a direct evidence of this chain scission, and we want to cross-link these analyses with the mechanical behavior to better understand what happens during the sterilization process and to better understand how to enhance properties where it is needed. We also want to go for a life cycle analysis, or we're actually doing it right now. In the next days, it will be finished. We want to see the environmental impact of our MACS process. And the most important thing is we want to do some comparisons. Because right now, I told you before, the preferred option or the normal option is high temperature incineration. We want to see the environmental impact of high temperature incineration, and we want to compare it with the combination of our MACS process and the waste to energy incineration. And we want to compare it with the most preferable option, combination of our MACS process and a mechanical recycling. We would like to prefer the mechanical recycling because this is the most easy way and the way that has the lowest environmental impact. So we want to see what happens there. We want to compare this. and show you whether it's worth or not to think about this. And last but not least, we really want to close the loop. We are in close contact with some sorting companies, and we want to take our waste that comes out of our MACS machines and want to go to a sorting plant, and we want to sort different fractions out of it. And we want to take some of these fractions and go to a regranulation step where we can use all the knowledge we gained in the tests I showed you in the previous slides, and the results from the tests that will follow, to get a good recyclate, to get a good regranulation. And then we want to investigate this regranulate again, and we want to go to the market and see how the pricing will be, how we can sell it, how it will work on the market. I'm not personally at my end, but I'm at the end of this talk. So thank you for your attention. And if you have any questions, feel free to ask. I'm here for your questions. I was told that I have to be on time, so I speed it up a little bit. So we have time for your questions. Thank you.